the equations of fluid dynamic type equations which are obtained as a continuum limit of the Boltzmann equations. Continuum limit means that the Knudsen number or the Knudsen number go to 0. That means the collision term of the Boltzmann equations become important. And Knudsen number equal to 0 is a singular point of the Boltzmann equation. Therefore, if there is another parameter in the parameter, then if you also make some limit together with the Knudsen number, the result different depending on the relative speed of the two parameters go to 0. Today, I want to discuss this type of limit. There are, you can imagine various cases, but one of the most important cases is the case where the some boundary parameter changed. For example, we take the flow between two cylinders. And this is the space between the cylinder, and this is the radius of the curvature, the radius of the cylinder. And if we take the d over L's go to 0, okay? And this is the curvature go to 0, the cylinder radius getting infinite. Then they become flat, okay? Two parallel plates. We consider that case. Then, depending on the speed, that the curvature go to 0 and the Knudsen number go to 0, the result is different. And there are very important result from that one. Okay. Okay. Take a gas between two coaxial cylinders. Radius L and the other is L plus D. The gas flow is nearly parallel. We consider the case nearly parallel flow. Okay. Therefore, if we take the limit, then it becomes two parallel flow, simplest one, the wet flow. And the Boltzmann equations is given here. Okay. The K is essentially Knudsen number. Okay, the two boundary conditions on the cylinder, this inner cylinder is the outer cylinder. Then we take the limit of Knudsen number go to 0. This is the L over D go to infinity. Okay. Then we consider the case D over L is scale of the Knudsen number. C is some constant, okay? Depending, we consider this case. The reason why we take this case is this is the threshold of some effect. Okay? And we use the cylinder coordinate r theta z. R equals 0 is the center of the cylinder. Okay, and they are non-dimensioned by the space of the two cylinders. Okay, then we use the notation x is this one, and the y is this one. The z is this one. And zeta x, this is the molecular velocity in this way. Okay. In the limit, Knudsen number go to 0. Knudsen number go to 0. X, y, z is reduced the Cartesian coordinate. They are practically the cylindrical coordinate. X, y, z practically cylindrical coordinate, but in the limit of Knudsen number go to 0. Knudsen number go to 0 means that d over L go to infinity. Okay. In this limit, it reduced to the Cartesian coordinate. Okay. But however, be careful to the higher order quantity. Okay? Nearly parallel flow means that the flow in this direction is order 1, and the flow is this direction is order k. And mass conservation, from the mass conservation, that the derivatives along the flow should be small. Okay, and in this direction, this is order of f. Okay, we consider the solutions in this. Okay. In this framework, Knudsen number go to zeros, and we consider this type of flow. I want to go to the next slide. Yes. No. Oh, okay. I want to next. Okay. We can, for small Knudsen number, we carried out the Hilbert expansion, that the distribution function expanded in terms of the Knudsen number, and with additional condition. With the additional condition means that the curvature also goes to 0. Okay. And with some speed, the curvature goes to 0 with the speed of the square of the Knudsen number. In the Hilbert expansion, macroscopic variable also expanded in the Knudsen number. The main flow is started from the order 1. Okay, the other component start from the Knudsen number. That is nearly parallel flow. The pressure started reading order 1, and the temperature started at reader 1. If we carry out the Hilbert expansion, we get the fluid dynamic type equations. I will explain later explicitly, but this fluid dynamic equations, starting with this type of expansion with additional curvature condition, then that equation is some reading, the equation that determines the reading of the parallel flow velocity, main flow velocity, is determined together with a higher order quantity. Okay, this is Knudsen number quantity. This is the solution is determined by the staggered combination of the variables. Therefore, you have to know this. You have to know this one. That these two are related. Therefore, you cannot determine the solution independently of this one to that one. This we call the ghost effect. And the equation also contains the non-Navier-Stokes stress in the equation to determine this quantity. We are only interested in the leading order term, but we have to know this quantity, or there is non-Navier-Stokes term. Yeah, it doesn't. Oh. That's interesting. If we carry out the Knudsen analysis, we get the boundary condition of fluid dynamic equation. But I don't want to say so much for this one. Next, how we can go to the next slide. Today, I want to stress on the ghost effect, not on the non-Navier-Stokes effect. We consider the simpler case where the Mach number flow velocity is small but finite. That the Mach number is small but much infinitely larger than the Knudsen number. We consider the case, first take the Knudsen number go to 0, and then take the Mach number go to 0. Okay? Therefore, main velocity, that we take the small parameter epsilon here, and this is the main flow, the main flow of all the epsilons. This is the quantity of the order of Knudsen number. They start at the leading order term. Pressure, the leading order terms is expanded in mean free path. The second subscript means this expansion. And this is the pressure of the Knudsen number squared. That starts this way, and the temperature and the density. And we also, this constant is scaled this way, okay, for small mean path. And also the slow variation in the directions of the flow direction, we take this factor. K over epsilon. Epsilon small, but the K is much smaller than this one.
Epsilon is a Mach number.
Mach number. Mach number. And the x, y, z is the Cartesian coordinate in the limit with x being in the channel directions and non-dimensions by d. Cartesian coordinate, you must be careful. This is the Cartesian coordinate in the limit Knudsen number go to 0. Okay. Then we get the fluid dynamics equation for x, y, z, and tau. This is practical temperature, and this is practically x shrinked coordinate in x direction, x, y, z, t. And the non-slip boundary condition. For this variable, we got a non-slip boundary condition. Okay. That equation is the following equation. Okay. The following equation. This epsilon terms of the pressure terms this way, and this is the constant, okay? And then the epsilon square term of pressure it is independent of y and z, okay? And this is practically solenoidal relation. You know this type of this equation very familiar. Okay, this is the conservation of mass equation in the present state in that way. This comes from the order of the Knudsen number. This is come from the Knudsen number. This comes from order 1. And then the next three. This is the momentum equation. And this derivative says very familiar forms of the derivative. Okay, x, y is just a shrinked coordinate. Okay, and then this acceleration term, the pressure gradient. Note that this is 2. Okay, and then this is the Laplacian two-dimensional Laplacian. They don't contain the x2 derivative. Okay, and in y directions, this is common, but this is also nearly the same thing. But you must note that this is 2. Okay, second order of Knudsen number. Okay, and you have these variables. In the limit, it is a it's a Cartesian coordinate, but this comes from the higher order solvability condition of the Boltzmann equation. Therefore, that contains this term. Okay, in the cylindrical coordinate, you know that these terms already very well in the Navier-Stokes equation, but in the limit, this is the Cartesian coordinate. And if you determine this quantity, you have to solve together with this one. Okay. Therefore, in the limit, this Cartesian coordinate velocity, this term enters. Okay. That is the main things. And this is the z direction perpendicular to the blackboard. Then same form, but they don't have, naturally they don't have this term. And the pressure term, temperature term like this way. Okay. This is the small Mach number case, but you must, even in that case, if you start from the Boltzmann equation, we are treating the gas. Therefore, it is not the same. It is not the same as the energy equations of the incompressible gas. There is a difference from the incompressible Navier-Stokes equations due to the contribution of work done by pressure. Therefore, what we want to know the parallel velocity is determined together with the infinitesimal velocity space. This is the ghost effect. Because if you consider the limit of Knudsen number equal to 0, then say you don't know you cannot measure this quantity directly. Okay. Therefore, but this is affected by this quantity. In such sense, it's a ghost effect. Okay. And note that these are the Cartesian system in the limit of k equal to k tend to 0. Note that these are the order of the k, and the momentum equations in the y and the z directions are the solvability conditions, are from the solvability condition of the order Knudsen number. Then naturally they are not the Cartesian systems. The infinitesimal curvature effect of x component contribute to the Cartesian y component. That is the x square term. Okay, in the x y component of the momentum equation. However, in the limiting ux is the same as the Cartesian x, okay, and is subject to the effect of infinitesimal curvature. They subject to the terms effect of this term. Okay. Okay, look at this one. Okay, there is the curvature of the boundary. The flow is parallel to this direction. Therefore, this is the main flow. Okay, the main flow have this component, infinitesimal this component. Okay, therefore, in the original coordinate, the uy is a component, but the real in the Cartesian coordinate there is another contribution from ux. Okay, therefore this ux enter that momentum equation. Okay, that is the equation. That equation is somewhat I want to back to the equation. Another one step back. Okay, this equation rather strange forms. Okay, it is similar to Navier-Stokes equation, but the pressure in the pressure, this pressure and this pressure is different. Okay, this is the leading order pressure, and this is the 2 means Mach number. Okay, this 2 is the Knudsen number. Instead that this pressure, y and z component, it is independent y and z coordinate. Therefore, this equation are a little bit different forms of the original Navier-Stokes equation. Therefore, later I want to talk how to consistently obtain the solution of this equation. Okay? Pardon? P20 and P02 is different. P02 is that P0 first subscript means that it's an expansion in Knudsen number. Okay. Second subscript means that it's an expansion in Mach number. But pardon? P20 should be determined to this equation. Okay, I'll tell you how to solve this equation later. Okay. Okay, thank you. And then before we explain how to solve the equation, but I want to show some interesting example. Okay, consider the bifurcation Planck-Wet flow. There is the Planck-Wet is the simplest problem of fluid dynamics, and this is thought when you get the Navier-Stokes equation, the simplest example is this flow. There is the two plate, and the lower plate is moving in the direction parallel to the wall. And in the compressible Navier-Stokes equation, flow field is a linear profile like this way. Okay, and we want to consider the bifurcation of this flow. Okay, in the Navier-Stokes equation, it is mathematically proved that it is linearly stable for the whole Reynolds number, and the people do not find bifurcated, how the solution bifurcated. Okay, and I don't skip I want to skip the details of the analysis. But if you just put as a part of the forms of the, if you part of the expansion of the bifurcated solutions, if you consider the flows is periodic in this direction, and put that forms and try to find the bifurcation. Then this is the d direction. Okay? This is the d direction, then after bifurcation we find this type of. After bifurcation, we have this type of flow in the YZ plane. Okay, these three is for different parameter. If we move away from the bifurcation, that if we accelerate the speed of the walls, then the flow like this way. Okay, and this way. This is the infinitesimal, but this is of the order of the Knudsen number. Therefore, Knudsen number goes to 0. They vanish, but this is the infinitesimal. And for z equals 0, they are upward flow, and for z equals 1 is downward flow. We consider the periodic solution, so that is periodic with for 2. Okay. Then you can consider the many type of solution, but for this case we have this type of solution. Okay, then according to this flow, originally before bifurcation, this is a straight line, okay? Straight line. At z equal to 0, z equal to 0, the flow velocity, x component of flow like this way, okay? That means the flow is accelerated, okay? That means that the flows going from down to top, then the faster flow moving to the top, then the flow is accelerated. On the other, z equal 1, the flow is going down, then the flow is slower flow going down, then they are decelerated. Farther away from the bifurcation point, then the deformations of the profile of a parallel component and bigger and bigger. Okay. In this, but this is the limit of Knudsen number equal 0. Therefore, at that moment, you don't perceive the other component. Okay. In this way, we have the bifurcations of the flow. This is the example. Okay. 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 I repeat again. Said if you can get a similar type of equation if you start the Navier-Stokes equation in compressive fluid for velocity field. Rather insistently called for velocity field because our equation is our energy equation different from the incompressible Navier-Stokes equation. The limit of Reynolds number goes to 0, which radius this radius over space of the channel. Then this is order of the Reynolds number scale. Okay, then we get the same home equation with the Gauss effect equation we have shown on the slide. Okay, then we have the bifurcation of Planck flow. On the other hand, the classical result is the Romanov studied the linear stability of the incompressible Navier-Stokes equation, and they found that the solution is stable for all Reynolds number. But depending on the speed of go to zeros for compared with the Knudsen number, we have the bifurcation. Okay? Therefore, in this way, we can find the bifurcations of this one. Now we go to the how to we obtain the solution. Okay, and that equation is a first order equation. Then say, and also there is a solenoidal relation for these variables. Therefore, first we assume that this is given. Okay, and this velocity field satisfies the solenoid condition initially. Then you integrate the equation for parallel velocity that contains P02 over the cross section. You have this this type of condition. Sorry. This is the conservation equation over the cross section. We get this mass flux conserved along the pipes. Okay. Then this is the pressure conditions, and this is mass conservation equations, and this condition. We integrate the momentum equation in the parallel directions. Can I go back 2 slides? 4 slides. Sorry, one more. Okay. First we integrate, then we get the equation we have shown. Then next we integrate over the space, okay? Integrate over the cross section. Then we get the this equation, okay? And the second derivatives P2 is like this way, okay? You integrate and you take the differentiation. Then for this differentiation, using this time derivative terms vanish, okay? Then we get the bar is the average over the cross section. And these are known, okay, at this point. And if the p value of p and its derivatives are known at some point, then we know this for all the points, okay? This is the same thing as the classical fluid phasor flow. Phasor flow, if you give some pressure at some point and the pressure gradient at some point, then you know all the the pressure field. And we take this case. You specify the pressure or pressure gradient at some point. Now we take the divergence of the momentum equation as you do in the Navier-Stokes equation, and then from the condition that from the solenoidal condition, you get the time-dependent term disappeared. And you get the equations after some manipulations, you get this equation. Okay, I want to return to the same equations, that 6 or 7. Okay, this equation. You take the divergence here from this equation. Then you have this equation, the pressure time-dependent term vanishes. And if you also have the non-slip condition of the boundary, and then you know already this, okay? I have shown that this. Then you get that this is time divergence, this square, okay? This is square, and all the knowns at this point, okay, and return to the okay. Then we get this equation, okay, and this is this function is this is the functional of ux, ui, uz. And their space derivative, they don't contain any time derivatives. Okay, in that sense, this is known. This is Fn is known because we are assuming that at this moment these are known. Okay, this is the Poisson equation. Okay, and then. Let the normal to the variance. This is x component equals 0. This is normal in this. Be normal to the boundary, and you multiply these three, you make the scalar product of the momentum equation with this one, and the flow velocity, this component, this is equal to 0, then you get the this condition. Here again, so you have also this multiply time derivative term also vanish. Okay, and then this is the boundary condition of the Poisson equation. From that, P2 is determined with the additive function of this x variable and t. Okay, but the P2 determined with this condition. But this ambiguity has no influence dp to 0, dpy, and dp2 and dpz in equation, in the momentum equation. Okay, then all the term except these are known. Okay, therefore at the moment where t equals t0, these are determined. Okay, and owing to the conditions of the P02 satisfy the Poisson relation, that come from the dt, time derivative vanishes. To make the time derivative vanish owing to the solenoidal condition, then we get the equation P02, Poisson equation P02. Contrary, in this case, we know that if P02 satisfies the Poisson equation, we get this condition. Okay, therefore, initially, if you know that these variables, then next time steps these quantity are determined in a way that they are satisfied. Therefore, in the next step, that ux and uy, uz that obtained now satisfy the solenoid conditions in the next step. That determines the solution. In this way, we can determine the solution consistently. Okay? In such a way, okay, again another. Okay. Yes, equation, that equation. We can consistently determine the solution of this system. Initially, we get ux, ui, uz in such a way that satisfied solenoidal condition at the point at some given time. Okay, and then from that we discussed this term. Okay, and from this equation, by integration over the space and cross section, we get the equations of the taking and integrate these equations and taking a derivative, you get the equations of the P2. In this process, what is important? This is the P02 is the independent y and z. Then, if you integrated it, that just P02 come out. Okay, other part you have to take the average. Okay, then if you give the value of the P02 and its derivative, then P02 is determined. Okay, next step you take the divergence of this equation. Then from this condition, the divergence time derivative vanish, And then you get the equations. You take the divergence and take the average over the cross section. Then you get the equation for this one. Okay. Then say if you get the and you solve the this equation, then from that you know all the variable here. Okay. And you then you know the time derivative terms. Therefore, you know the solution of the next step. But the solution of the next step satisfies the divergence-free condition because you choose this as a Poisson solution of the Poisson equation. That means that the time, if it satisfies this once, then this divergence of this term vanishes. Okay, we choose P02 in that way. Therefore, we consistently obtain the solution in the next step. So is my talk today.